Hey folks, a couple of things to announce. I posted a quiz for you that's due on Friday at midnight. I don't know that I'm going to post a reading assignment because I'll probably post a second quiz. Right now the quizzes are sort of the most important thing, or as far as your grade's concerned, those quizzes are the most important thing. Now, I've had a couple emails about how to calculate your quiz grade. What I do is I take the total number of points that you've earned, and that's on Moodle to date. I think the maximum was out of 73. Is that what I said? Yeah. So the way I calculate that is I just take the value, that's the number of points that you got on the quizzes, and divide that by 73. And then in the end, I'll take that percentage, and that'll be your percentage for that grade. So it'll be out of 100 points. So if you have an 82% right now, that means your exam number 5 will be at 82%. Now, as we go along and take more quizzes, then the maximum number possible increases, but then also so does the number of points that you gain on those quizzes. Each question counts 1 point, so as they add up, you can just add those points to that total. If you have questions about that, please let me know. I can help you and sit down and we'll go over the numbers with you. Okay? Also, I handed back your exam 3. It's important that you hang on to those, or at least that you know where they are online, even if you don't have exams 1 and 2. But the final exam will be made up from those 4 exams that we take this semester. Not from old exams, but I tell students just to study this semester's exams. They're not exactly like those questions, but I'll start with those questions and I'll change them up in various ways. In some cases, I'll just change the numbers so that you get different values. In some cases, I'll change them a little more substantially, but you'll still be able to recognize them as the question that you saw before. Okay, so if you're beginning to think about the final, you can go back. Now is not a bad time to begin to think about the final. It's not that far away. Go back and work through exams 1 through 3. Maybe just take 5 questions a day and work through those. Say, I'm going to spend 15 minutes a day here preparing for the final. Typically, the final average is a little bit higher than the 4 exam averages. So I'm not saying that every student does better, but overall, students do better on the final than they do on the hour exams. Okay? But that's overall. That's like as a class. So that might not be true for you. You need to be preparing now. Okay? We're having our lunch today. I sent out an email at the Ask the Prof lunch. So if you guys want to come, we'll meet at noon in the conference room. You can bring your lunch or not. That's fine. But we'll probably be eating lunch. And there's something else I wanted to tell y'all. Oh, the food drive. The food drive, y'all coming along pretty well. There's a link on the web where you can see how we're doing. I think I showed this to you. We're at a little more than 300, so that's good. I expect that we'll get to 600 by the end of the week. So if you haven't brought in anything, bring in 3 to 5 cans. 5-ish is sort of what I was thinking. Bring in about 5 cans. Go through your pantry or go to your family's house or whatever. Go through their pantry and pull out things that you haven't eaten in a while that's not expired, but that you might not eat. And then bring it, or go to the grocery store and just pick up a couple extra things while you're shopping. And then just drop it by my office. Just to remind you, this counts as 10 points for the whole class. So it's a group effort, and a lot of y'all have been bringing in stuff, and I'm glad. I mean, we have 300. We're about halfway there, a little more than halfway. I fully expect that we'll get to 600, but I would like to have as much participation as possible in the class, okay? Many thanks to y'all that have already brought stuff in. I mean, some of you have brought in a lot more than 5 items, and, people will be grateful to you for that, and I'm grateful to you as well. All right, any questions about the food drive and sort of how that counts? That 10 points just sort of goes into the pot. There's a pot with 700 points in it, and it just goes into the pot. You can think of it as adding to an exam or your quiz or however you want to think of that. Okay? There will also be an online assessment you'll be getting notice of at some point later in the semester that you'll take. Participation in that will be 5 points. And as I said, it won't be graded. I mean, I'll see the results, but your number of points won't depend upon your performance on it. But I do ask, and I asked you, as a favor to me, that you spend time on it, that you set aside 20 to 30 minutes. Many of the questions you'll see are familiar. And some of them might be unfamiliar, but you should be able to answer them, I think. All right? As a favor to me. You'll do your best on it? Yes, because y'all are awesome. That's why. And you don't need to have points to do well on something. You can just do well on it just because you're awesome and smart. Okay, let's sort of recap what we were doing. We looked at moment of inertia last time. Remember, moment of inertia describes the inertia of a rotating body. Just like a body that's traveling in a straight line has inertia that's measured by its mass, an object that's rotating has inertia. We call that rotational inertia, or the moment of inertia. And remember, it's not only dependent upon the mass, but it's dependent upon how the mass is distributed. And we'll see when we get into angular momentum how figure skaters, they change their moment of inertia, right? You ever seen figure skaters or dancers do this a lot? How do they change their moment of inertia? What now? They squat? Is that what you said? Okay. They change the way their mass is distributed. They'll throw out their arms or their legs. What they're doing is they're changing their moment of inertia, and that affects how they rotate. So we'll talk about that in a little bit later. Let's look now at Newton's second law, and as it relates to angular motion. For just a second. Okay, so we saw Newton's second law in chapter 4, this whole F equals ma. F equals ma. Now, just to remind you, remember we've seen this before, but where we had x before, we now have theta. Where we had v before, we now have omega. Where we had a before, we now have alpha. Where we had F before, we now have our torque. Our torque is sort of like an angular force. We can think of it in that way. And where we had mass before, now we have I. This is our moment of inertia. So as we're running along and we're making these comparisons to the translational or the linear frame to the rotational frame, now we can add one more arrow into that quiver. That my mass I can now think of as moment of inertia. They're not the same, but mass and moment of inertia are very similar. They describe that reluctance to change your state of motion in inertia. So we'll see, as we have Newton's second law, we'll see also that Newton's second law also applies in circular motion. And since the moment of inertia, I'm going to call it mom of inertia, is a measure of the rotational inertia. And the angular acceleration, that's alpha, is the rotational acceleration. Then it shouldn't be a real big step for us to say that where we had F equals ma, now we can have torque equals I times alpha. All right, remember torque is Newton meters. We can just sort of look at the units and make sure that this makes sense in a unit sense. This is Newton meters. That's going to be kilogram meters squared per second squared. My I is mr squared, so that's going to be kilogram meters squared. And then my alpha will be 1 over second squared. So these do have the same units, and as you know, you need to know how to determine the SI units for any of these quantities in this way. But our torque is equal to the moment of inertia times alpha. These are vector quantities. Torque and alpha are both vector quantities, so we can put arrows over both of them. And when torques are in the clockwise direction, those are considered to be negative. And when they're in the counterclockwise direction, those are considered to be positive. Now remember what we talked about with that. We saw this on the last exam, and it'll come up again. Let's say that I have a bar that's rotating about this point, and I apply a force in this direction, or I apply a force in that direction. Both of these forces are going to cause what? clockwise motion. So these would be clockwise torques. And if I have a force over here, this force would be a counterclockwise torque. So as we did on the last test, you'll need to know how to do this again, because we'll see systems, not necessarily a bar, but maybe a disc or a cylinder or something along those lines, the shapes that we saw on our table that we did last time. Remember the table with the sphere and the bar and the cylinder? We'll have different forces applied to those objects that will cause different torques, be they counterclockwise or clockwise. You'll still need to know how to do that for this upcoming exam. Let's do an example. So let's say that we have this disk, and it's allowed to rotate about its central axis, and it has a mass of 1 kilogram. I want to know first, what is its angular acceleration, and then also what is its angular velocity after 3 seconds. You shall have a problem that's similar to this, where if you change the, hold on. You shall have a problem similar to this, where you have forces that are acting on an object, causing it to rotate, and I ask you questions about what is the net torque acting on the object? What is the acceleration of the object that's caused by that torque? What is the angular displacement, or what is the angular velocity after a given amount of time? Look back at the old test, there are examples like that throughout, and we'll work through some in class, and you have some in your homework too. But let's work through this one. I want to know, what is its angular acceleration? The angular acceleration, remember, is alpha. And I want to know, what is its angular velocity? That's omega after t equals 3 seconds. It has 2 forces acting upon it. So I'll want to find now what is the net torque. So your steps here, first we'll ask ourselves, what is the net torque? Then the second step, we'll ask ourselves, what is the moment of inertia? And then the third step, we'll ask ourselves, what is the angular acceleration from Newton's second law? And then the fourth step, we'll ask ourselves, after 3 seconds, what is omega? So we'll go through each of those steps. On a test, you'll see there's probably a couple of questions. Just like with the bar, I have this object that's allowed to rotate about this axis, and I have 2 forces. You'll want to find out which of those forces gives a clockwise and which gives a counterclockwise. This force will cause the disk to go counterclockwise or clockwise. Clockwise, very good. Because if I have this force, it causes it to rotate in this direction. So this force causes it to go clockwise. On the other hand, this force causes it to go counterclockwise because it goes in this direction. So this force is a negative torque. I'll call it negative torque 2. And this torque is positive torque because this one's clockwise and this one's counterclockwise. So, part 1, my net torque equals torque 1 minus torque 2. Now, the moment of inertia, excuse me, not the moment of inertia, the moment arm, remember that's the distance from the axis of rotation to where the force is applied. In both of these cases, it's 1 meter. That may or may not be the case for your device, whatever it is that you encounter on the test. It'll be something similar to this, but it could be a cylinder, it could be a bar that could have different forces applied at different distances. Kind of like that question that we had on the test with the bar with the 2 forces acting on it. So torque number 1 is force 1 times R1 minus force 2 times R2. That's going to be 1 Newton times 1 meter minus 2 newtons times 1 meter. And that's negative 1 Newton meters. Okay, so that's my net torque. Now I want to know what is the moment of inertia. And this is really, you need to go back to that equation sheet that you'll have on the test and the table that I showed you and figure out what is the object that we're talking about. In this case, it's a disk. So if you look at that table that I gave you with all those different shapes on it, you can either look back a few pages or go to the equation sheet in the back and tell me what kind of object is this that's listed on that equation sheet. No, the 2 newtons isn't negative. In fact, if we look, she asked, wouldn't we add the 2 newtons here? Because this force negative. I'll just give you the magnitude of the force here. So it doesn't have a negative value. The negative only comes about because it's a clockwise torque. All right, the force will never be negative. Even if the force is pointed downward, we don't think of it as negative. We just think of it as providing clockwise or counterclockwise. That's a good question, though. I could see how you might be confused, because if the force is labeled downward, then you might think, oh, well, isn't that force negative? But when we're talking about rotational motion, that's never a concern. It's only is it clockwise or counterclockwise. Okay, so back to my original question. What kind of shape is this from that table? It's a what now? Not a solid sphere. No. It's a what? It's not a hoop or a wheel. It's not a thin-walled sphere. It's a cylinder. All right, people always mess this up because it's a cylinder. It's just a really flat cylinder, right? It's not a hoop or a sphere because a hoop is like a hula hoop, right? And a thin-walled sphere is like a basketball. It's a sphere with nothing in the middle of it. And a solid sphere is, I don't know, like a pool ball or whatever. So we determine that this object is a cylinder. It's really just a really flat cylinder. And on that equation sheet, the moment of inertia for a cylinder is equal to, I think it's 1/2 mr squared. Am I right about that? Okay, so you have to figure out the right equation to use, and then we can calculate, then, given the mass and the radius, the mass of this cylinder is given, it's 1 kilogram. So 1/2 of 1 kilogram times 1 meter, it's squared, and that's equal to 1/2 kilogram meter squared. So now we find our moment of inertia. Now we want to find what is alpha. And this is where our Newton's second law comes in. I have this object that has a torque applied to it. It has a certain moment of inertia, and then I can find its acceleration. This is the F equals ma of rotational motion. Remember, our torque is like an angular force. This is like an angular inertia. This is our angular acceleration. It's our F equals ma. And we can use it in the same way. I can find my alpha is torque over I. That's going to be, go back and find our net torque. It was -1 Newton meters over 1/2 kilogram meter squared. The moment of inertia can never be negative, in the same way that mass can never be negative. And that's equal to -2 radians per second squared. Now, we have all SI units here. So my alpha is going to come out in radians, which is our SI unit. Whenever you're dealing with Newton's second law, your alpha has to be in radians. It can't be in revolutions. It can't be in, what's the other one? Degrees, right. It can't be in degrees. It must be in radians. Okay? However, if you're using your calculator, you think, oh, do I need to put it in radian mode? Do you need to put it in radian mode? No, never for this class. That only comes into place if you're taking the sine or the cosine or the tangent, a trigonometric function of an angle that's measured in radians. But we won't do that. We'll always use degrees for those angles. Okay, so that's our alpha. And then the final part of this question is really just applying the kinematics equations. I think in this one, I asked for omega. Yeah, after 3 seconds. But I could also ask for theta. Omega is omega naught plus alpha t. Omega naught was 0 because it was initially at rest. I have -2 radians per second squared times 3 seconds. And so that's -6 radians per second. That's the angular speed after 3 seconds. But we could also ask what is theta. It's equal to 1/2 alpha t squared. I left off the omega naught t because omega naught was equal to 0. And so that's 1/2 of alpha, which is -2, times the time squared, 3 seconds squared. And so that's -9 radians. Okay, either one of those. You'll see a similar question. We'll see one. We'll probably work one in a bit that's similar to that. Similar, but different, maybe a different shape, different forces acting at different moment arms, but still very, very similar to that. Okay? Y'all could do that right now on the test? Do pretty okay on it? Yeah? Practice a little bit on it, because you will see it. May I go down from here? All right. I think there's a quicker question on the next page. Oh, no, there's not. Let's go to the back, though. We'll do a practice. Okay, look, here's a good example. Let's do number 7 and 8. This is on, well, y'all don't have page numbers in the back, do you? But this is exam 3, I think. No, exam 4, 7, and 8. We'll do number 7 first. Here you have a hoop. Want to know the net torque that acts on that hoop. Oh, I remember what I was going to tell y'all. Registration starts today for those, the special people, the people that are athletes. I mean, you're all special. Right, graduating seniors, I think, honor students, various people. So if you're registering for physics and you have any trouble, just shoot me an email. And also register as early as you can. Now, we have an extra section of lab, so I don't foresee there being any issues with lab. But as you know, some sections of lab are more popular than others. So if you want to get that section that you really want or need or whatever, then register as soon as possible. Right now, there's spots available in all the labs, but just be aware that you need to register as soon as possible. What is the net torque on this thing? All right, we'll stop in just a few seconds. I'll stop at 103, or I'll go to 105. Nope. 105, D is right. I first figure out which is positive torque, which is negative torque. This is a negative torque because it's, that's positive torque because it's counterclockwise. This is negative torque because it's clockwise. I'll call this torque 1, torque 2. You say 30 newtons, that's our force 1, times 1 meter minus 10 newtons times 1 meter, and that gives us positive 20 newton meters, which is 20 newton meters clockwise. All right? So that is right. Oh, what's the difference between, if I can get this right, what's the difference between a piano and a tuna? You can tune a piano, but you can't piano a tuna. Oh, that was good. All right, let's do number 8. After 2 seconds, what is the net, this net torque acting, what is the rod's angular velocity? So a couple of steps in this, you need to figure out its moment of inertia, and then figure out what is its angular velocity. Doing pretty well. A few of you have the wrong answer, so ask your neighbor if you like. See what they put. All right, we'll stop at 110. 110. Let's see. I'm not sure. So I know that my torque is 20 Newton meters. We found that in the previous section. And now I need to find what is my moment of inertia. Well, this is a hoop, right? Like a hula hoop. And the moment of inertia of a hoop, if you look on that equation sheet, is equal to mr squared. All right, you'll need to look on that because, I mean, if you know it, that's fine, but you should look. It'll be there for you. The mass was 2 kilograms, a radius of 1 meter. So 2 kilograms, 1 meter. That's squared. Make sure you get it squared. It doesn't matter here, but it does matter generally. So that's my moment of inertia. And then I figure alpha is torque over I. That's going to be 20 over 2. That's my torque divided by my moment of inertia, which is 10 radians per second squared. And then after 2 seconds, omega is equal to alpha times t, which is 10 times 2, which is equal to 20. So D is the right answer. Awesome. Sorry I doubted you. But it is 20 radians per second. Be careful, make sure you check your units, because if these units are in revolutions per second or degrees per second, you'll need to change. Usually in the text of the problem, I'll try to make that clear that in revolutions per second, I'll say, give the angular velocity. In this case, it was just radians per second. You shall have a couple problems on the test similar to that. It'll be a different shape probably, different forces. Your forces might even be at an angle like we saw in that bar, but it'll follow the same procedure where you find the net torque, the moment of inertia, the angular acceleration, and then whatever it is else that we're looking for. All right, let's look at energy. Objects can have two types of energy. They can have translational energy. That's like what we've done before. But then they can also have rotational energy. And this type of kinetic energy, this is called translational. And that is just the energy of something moving in a straight line. So if an object has a speed and it has a mass, then it has a translational energy. And it's the kinetic energy is 1/2 mv squared. So you can probably imagine what is the rotational kinetic energy. The rotational energy is equal to 1/2. Let's see, what is our analog to mass, the inertia? The I, so 1/2 I, and then our analog to V is omega. So the same is here, 1/2 I omega squared. That's our kinetic energy. Sometimes if you have an object that's both spinning and traveling in a straight line, like for example, I can take this and I can make it spin and travel in a straight line, then that's going to have both translational energy and rotational energy. In fact, on the OpenSex quiz, I'm pretty sure I put a question there where it asks you, what is the total energy? So just remember that if I have something that is spinning and traveling up, it can have both the total kinetic energy will equal to the rotational energy plus the translational energy. It's going to be that 1/2 I omega squared plus the 1/2 mv squared. So you need to know both its rotation rate and the speed at which it's traveling to find its kinetic energy in the linear sense and in the rotational frame. So the mass, which is a measure of an object's inertia, is replaced with the moment of inertia. That's that I value, which is a measure of the object's rotational inertia. And the velocity, or the speed rather, for kinetic energy, is replaced with the angular speed. So we have m becomes I, v becomes omega. All right? Now the work energy theorem says that when you do work on an object, you increase its energy. Remember we said this was work equals a change in energy, or a change in kinetic energy in particular, as what we're talking about, a change in kinetic energy. This also applies for rotational motion. So a couple of things. First of all, if you recall, for work, my work was equal to force times displacement. So what do you think is going to be the expression for work in angular motion? No, not what is force times radius? Torque times radius. You're close, but not quite there. What do you think is going to be? Huh? That's right. Our work in an angular sense will be torque times theta. Work will equal to torque times the angular displacement. So if I apply a torque over a certain angle, then that will give me my work in a rotational sense. And then this work will cause a change in energy. Let's work through an example. I'll show you what I mean, how we can use this. So let's say that I have a hoop, a thin hoop that's rotating at 10 radians per second. There I get its radius and its mass. And I want to know a couple of things. I want to know how much work is required to stop it. And then let's say that, well, first, how much work is required to stop it? Excuse me. The work is our change in energy, or my change in kinetic energy. So really all that I want to know is what is the kinetic energy that this thing has, and then the amount of work that's required to stop it will be the amount of work that's required to take away all that kinetic energy. So it is going to be the kinetic energy. So I need to figure out what is the kinetic energy of this thin hoop rotating at 10 radians per second. First thing you need to do is find the moment of inertia. All right? So take a moment to find the moment of inertia for this hoop, and then figure out what is the kinetic energy. I'll give you a minute head start, then I'll come after you. What is I for a hoop? We did this before. It's mr squared, right? You can look on that table that you'll have on your equation sheet. It's in this chapter, but also on the equation sheet. The moment of inertia for a hoop is mr squared. That's going to be 1 kilogram times 1 meter squared. So it's just 1 kilogram meter squared. And then I want to know the kinetic energy. That's going to be 1/2 I omega squared, and that kinetic energy will equal to the work that's required to stop this thing. So that's equal to 1/2 of 1 times 10 radians per second squared. So that is 50 joules. You have to do 50 joules of work in order to stop this guy from turning. Now, let's say that I apply a torque Was that the end of that question? Oh no, also, what is the power expended? So remember, power is energy or work over time. If I do this over 5 seconds, I have 50 joules over 5 seconds, and that gives me 10. What is the unit for power? What is the unit for power? It's a lot, yeah. Okay, so that's our power expended. Let's also say, this isn't written here, but let's say if the torque is 10 Newton meters, what is the angle theta that it spins before stopping? All right, this will come up in your quiz, actually, your OpenStax quiz. But if torque is equal to 10 Newton meters, what angle theta does it spin before it stops? Well, I know that torque, or rather work, equals torque times theta. I know that it has to do 50 joules of work, this torque. If it's 10 Newton meters, what is my angle theta going to be? Through what distance, angular distance, will this thing travel before stopping? Not everybody at once. Feeling right now? Yeah, I think that's right. 5. Is that right? Yeah, so 50 joules equals 10 Newton meters. Times theta. And I solve that for theta, and I get theta equals 5. And it has to be in radians from here on out. When we're dealing with these equations that are mixing up our units, it'll always need to be in radians. Okay? Notice here, actually, that our units do match up. Work is in Newton meters. Torque is also in Newton meters. And theta is in radians, which is not really a real physical unit. So I have Newton meters on both sides of the equation. Okay, let's try this quick test. This one's similar to the previous one that we had, where you have to figure out the moment of inertia, and then you have to find... this isn't really an energy problem, but let's try it anyway. It's a good practice. Here I have a merry-go-round, give it its mass and its radius. There's a force, a single force applied tangentially. That means, along at tangent to the circle. Find the angular speed of the merry-go-round. Yeah, what would the merry-go-round be considered to be? It would be a cylinder. It's like a disc. Merry-go-round is a disc. And we don't have a merry-go-round in Thibodeau, travesty, but that is right? No merry-go-round in Thibodeau? That's gross. Doing well so far. About 5 or 6 of you have an incorrect answer. Feel free to ask your neighbor what they put. All right, let's stop at 2:05, or we'll go to 2:10. So just 10 more seconds. Guess if you're not sure. 5 more seconds. All right, A is right. Good. All right, so what we need to do here first is to find the torque. I have this disc. I have a force of 50 newtons applied here. It's applied at a distance of 1 meter from the axis of rotation. So the torque is 50 newtons times 1 meter, or 50 newton meters. Then also, I need to find the moment of inertia. This is a disk, so that's 1/2 mr squared. I just get that from the table. 1/2 of 100 kilograms times 1 meter squared. That's equal to 50 kilogram meter squared. And then I have to find alpha, which is torque over I. That's 50 over 50. That's 1 radian per second squared. And then I have to find omega, which is alpha times t. So 1 times 3 is 3 radians per second. As I said, you'll definitely have 1 to 3 questions that deal with topics like this on the upcoming test, which is on the very last day of class, by the way. All right. Sure. I go down now? Yeah. All right, awesome. We made it this weekend without my wife. We missed her, but we had a good time. Went to Chili's and hung out at Chili's. I had like the slipperiest burger that I've ever had. I had to eat it with a fork, because every time I'd hold it up, take a bite out of it, the entire patty would just slide out the back. It was strange. I never had such a thing, but it was pretty tasty actually. All right. Angular momentum, and we've dealt with angular momentum before, or we've dealt with momentum before. P is equal to m times v. Y'all remember this? P equal mv. So you can probably imagine what our expression for angular momentum is going to be. Because remember, we have something for m and we have something for v. So you're probably already thinking in your head, oh, this is just angular momentum. It's going to be. So the angular momentum is the product of the moment of inertia and the angular velocity. So we call it L for angular momentum. I don't know what it stands for. We just use L. And it's equal to I times omega. These are vector quantities. L and omega are vector quantities. Though largely we're not really going to deal with a vector, except we'll need to make sure that we get our positive and our negatives correct. Is it clockwise or counterclockwise? Is really, I mean, that's sort of dealing with it as a vector. And remember, you can compare this with the expression for linear momentum, which is P equals mv. So we've let our m become an I, our v become an omega, and our p now we just call it L. The SI unit is kilogram meters squared, that's I, divided by seconds. Right, this is my kilogram meter squared. This is my 1 over seconds, or radians per second. So that's our SI unit. And as we saw with linear momentum, you recall we saw with linear momentum that PI is equal to PF. We're going to have the exact same thing with this. We'll have LI is equal to LF. Or I initial, that's my moment of inertia, times omega initial is equal to I final times our omega final. Typically, or here we dealt with collisions. We're not going to deal with collisions in rotating objects. Instead, we'll deal with things that change their moment of inertia, going from the initial to the final state, and then we'll see that their angular speeds will also change. Let's go back. We'll go back. So, for example, you've all seen, you know, like we said, what do they call it? Ice figure skaters or dancers or, I don't know, people that spin around a lot. And when they spin around a lot, they'll bring their arms in and put their arms out. What do they do when they bring their arms in? What happens to them? They spin faster, right? Why does that happen? In terms of their angular momentum, what is happening when they go from I initial to I final when they bring their arms in? They're making their radius smaller. So remember, I, as that basic definition, is mr squared. If I make r smaller, then what happens to I? It doesn't go up, it does what? It goes down. If I make r smaller, so I can think of this as mr squared, that's I, times omega, equals mr squared, that's I, times omega. If I make this smaller, then this has to go up in order to balance, because your total amount of momentum is always conserved. Let's see, I brought... Wants to do this, somebody? I want to do this for me? Alan, you mind doing it? Sorry, Alan. Yeah. Just hold these and sit here. And I'm going to spin you around, so we hold your feet up above. And I want you to hold your arms out first. All right, like that. And I'm going to spin you around. And now bring your arms in. And bring your legs down. Can you feel it going faster? Yeah, it's sort of hard to see. Put your arms out. Oh, yeah. So bring your arms in. I'm going to spin you around again. And now put them out. You can see he slows down. He slows down because his arms are going out, and that increases his moment of inertia. And he speeds up when he brings his arms in because it decreases his moment of inertia and causes him to spin faster and faster. Let's try a problem like this. Clicker question. So in this case, I have a merry-go-round, and it's spinning, and this kid jumps onto the outer rim of the merry-go-round. And I want to know now, what is its new speed? So in my initial state, I have this merry-go-round, and it's moving at a certain speed. And then in my final state, this is initial. In my final state, I have this merry-go-round. It's still spinning, but now I have a kid that has jumped onto the outer edge of it. And what I want to know is, what is the new angular speed or the angular velocity of this object, this disk that's spinning after this kid jumps on? I want you to notice something here, that my units here are revolutions per second. I can keep them that because I see that my units are down here in revolutions per second. Okay, so what is the new angular speed? And you're looking at your conservation of momentum. That is that L initial equals L final. All right, let's stop at about 145. 145. Just 10 more seconds. Just guess if you're not sure. Okay, looks like most of you put D. Let's take a look. So, several steps here. First, we want to find out what is I initial. I initial is the mass of the merry-go-round, 1/2 mr squared. This is a disk. I look on my table. I find that the moment of inertia for a cylinder is 1/2 mr squared. And so I say 1/2 times the mass, which is 100 kilograms, times the radius, which is 1 meter squared. And so that's 50 kilogram meter squared. Now, the moment of inertia over here, remember, like with the Richard Pryor bit, where we have two pieces that are coming together, that's what's happening here. The moment of inertia of the disk is 50 kilogram meter squared. Now the tricky part on this is how to deal with the boy, the kid that jumps onto this merry-go-round. How do I treat him? What kind of shape do I treat the boy? This is probably where most of you got hung up on. How do I treat him? Not as a cylinder, no. As a what now? No, not as a ring. Do you treat it as a ring? And that would work. Now you treat the boy, remember before we did the moment of inertia for a system of particles, where we just had several particles rotating about an axis? We treat the boy like a particle. So he's like this mass that now sits on the outer edge of this. Now, Brittany, if you would have treated it as a hoop, then that would have worked, because it's like all of these masses at the outer radius. But we treat the boy as a particle, and as a particle, the mass is the moment of inertia is mr squared. And we did a problem like this earlier, where we had the three masses like this, and we just treated the three masses as mr squared to calculate the total moment of inertia. And so it works out that the boy, who has a mass of 50 kilograms at 1 meter radius, adds another 50 kilogram meter squared. So when the kid jumps on, it doubles the moment of inertia. So when I go from here to here, I get a factor of 2. So that means when I go from here to here, what's going to happen to the angular speed? Is it going to increase or decrease? It's going to decrease by what factor? 1, 2, 3, by factor of 2. Because my numbers would look like this. I would have 50 kilogram meter squared times 2 revolutions per second equals 100 kilogram meter squared times omega final. I add these two values to get the 100. And then omega final will equal to 1/2. What did y'all put? Oh, y'all put D. Oh, not 1/2. I'm sorry. You're right. It'll be 1. Yeah. So D is the right answer. Okay, folks. You'll have some of that. You'll have all those. You'll have kinetic energy problems. Oh, time to go. Okay, y'all have a great day. We'll finish up the quicker questions for this next time.